Okay, so a couple things to start out that Excel assignments due at the end of the day today. I've had a lot of people kind of email me the last couple of days with some questions, and hopefully it looks like a lot of you are on the right track and kind of getting things squared out. But make sure you get that submitted by the end of the night. I went back through in all the videos. I added some description of what they contain. So I was talking to a couple of students and kind of got this idea and thought that might be helpful, especially as we get closer to that exam when you're going back. If you want to review anything, kind of has a little description. I also, excuse me, under the lectures, I tried to give kind of a brief description there as well, kind of everything since the first exam. So hopefully that's helpful in kind of identifying where specifically things are. I'll start doing that from now on when I upload things, just to make it a little bit easier to kind of navigate. So we got that. And then we left off talking about how we do hypothesis testing and how we find p-values that eventually allow us to make this rejection decision, okay? So let's just kind of jump into an example, and I'll kind of do like a little bit of a review as we work through this example. I think I'll end up showing you a little bit in Excel today as well, and then we might jump back to proportions. So let's assume we have this problem where we want to establish whether the mean retirement age is greater than 67, right? So we've got a sample of 25 individuals. Sample mean is 71. We're told that the population variance, somehow we know that, is 81. What's the p-value for this hypothesis test? So we've got our sample, where is it? Our sample mean of 71, right? And we want to test for whether or not it's greater than 67. So right away, we want to test for whether or not it's greater than 67. What we want to test for is our alternative hypothesis. So we're thinking about, is this greater than 67, which makes the null hypothesis, right? It's the complement of that. So the null would be, there's a glare there, so let me see if I can for the video. The null hypothesis is that it's less than or equal to 67, right? Now, the type of test we identify off of the alternative hypothesis, right? So is it greater than 67? So we have a right-tailed test. So what that's telling us is if that assumed true value of 67 is in fact the true population mean, right? Our sample means should be centered around it. Okay? Now we saw a sample mean of 71. That definitely goes against the null, right? The null is that it's less than or equal to 67, and so we definitely saw some evidence that goes against the null here. But is it strong enough evidence to be able to reject this given the level of confidence that we want to have? And I forget the exact level of confidence, but I'll kind of show you at the end. It doesn't matter what, we could choose several levels. Right? So what we want to find is that if this was, in fact, the true population mean, what's the probability we saw something this far away from that population mean or anything further away, right? So 71 or anything further. That probability that I saw something that far away or even further from this assumed true value, that area represents our p-value. Okay? Now, if, let's assume for a second, this in fact ends up being the true population mean, anytime I see kind of a sample mean that's pretty far away, I might make a rejection decision when in fact I shouldn't have, right? And I'm okay with that because I know that if I see something here, the probability I see something that far away, if this was the true mean, is so low that I'm okay rejecting it because I won't be wrong that often. Right? I won't be rejecting it when I shouldn't have been that often. Okay? And when we reject it when we shouldn't, that was our idea of a type 1 error, or that was the idea that we're going to set some alpha. Right? So for a second, let's assume it's 0.05. I'm okay making errors 5% of the time, right? Alpha of 0.05 would be kind of the area over there, and I'd be making, if this in fact was the true population mean, I'll be making this amount of type 1 errors. Like the probability to make a type 1 error will be whatever alpha is, or I'll be making type 1 errors alpha times 100% of the time, right? So 5% of the time here. But if my p-value is less than this alpha, then that's telling me the probability I saw, the sample mean I did, or anything further, is whatever that p-value is. The probability I saw something that far away or any further. Well, how can I find that area? Well, if I have a normal distribution, I know my sample means, as long as the sample size is over 30, will be normally distributed. I can turn, right, that value of 71 into a z-score. Or, because we're not using a true population mean, we're using a assumed true mean, I can turn it into a test statistic or a z-statistic, right? It's still going to be coming from that standard normal distribution. It's just now that it's using that assumed true mean. So how do I do that? Well, actually, I can probably have that from here. Right, our equation for that z-score was take the sample mean that you found, subtract the assumed true sample mean, and here we'll divide by the standard deviation of our sample means. Now for this, we have an equation already, which is, that's just the square root of my population variance divided by my sample size. Right? So I can do this several ways. I can calculate this first, do the intermediate step, and then plug that into the denominator, or I can just plug that equation right in and do it all at once. Right? So we have to plug our values in here. I think we had what? I'll have to go back to the slides to remind myself. We had a sample of 25 individuals. Here I did one where I didn't have a sample size over 30, but if the original data was normally distributed, we'd still be okay, right? We only needed a sample size of 30 if the original data wasn't normally distributed. We had a population variance of 81, sample mean, and I'll get rid of alpha here for a second. This was 71, this was 67. So one thing we should start noticing is that anytime I see sample evidence that's above the assumed true mean, I should have a positive test statistic. Anytime I see something that's below the assumed true mean, then I would have a negative test statistic, right? And why? Well, it's because this numerator, right? If the sample mean I see is above the assumed true value, it'll be positive. If it's below the assumed true value, it'll be negative. And the standard deviation, what's my denominator? Well, standard deviations are always positive. Right? So here I see something above the mean. Automatically, I should know that I'm going to have a positive test statistic. Right? If I turn this into a z-value, it should be positive. Now, right away, what do I know this p-value has to be less than? What's the area to the right of the mean? 0.5, so I know this has to be less than 0.5. So if I go to the answers there, potential answers, right away I should be able to rule out B, right? I can rule that one out right away. So we have this z-score, right? You kind of think about, I'll draw it above it. We can draw it above or below it. It really doesn't matter. I'll turn the sample mean that I saw into that test statistic. Once I see that test statistic, I still want, right, it's a right-tailed test. I want the area to the right. I can look that value up in the table. The table will tell me the area to the left, right? But I want the area to the right, so I can just subtract it from 1. Okay? So if we plug those values in to our test statistic equation, we should get about 2.22, okay? So that's just, I had that up on the board, we plug those values in, we get about 2.22. I go to my standard normal tables, scroll down. So here's the 2.22, so right here. So the area to the left of that z statistic, that z value of 2.22 is 0.9868, right? So we've got 0.9868. To get the area that we want, we'll subtract that from 1, and we get 0.0132. Right? So our p-value, right, is 0.0132. Just need a little bit of space here. So our rejection decision is if the p-value is less than alpha. Right? If I have a p-value of 0.0132, can I reject at the 5% significance level, or an alpha of 0.05? Well, yeah, it's less than 0.05, so I reject. Right? Could I reject at the 1% significance level? There, it's not quite less than 0.01, right? That's the alpha for a 1% significance level, so I would fail to reject. Okay? Now, remember I said last class, we can think about, I've got alphas of 0.1, 0.05, and 0.01. That was the 10, 5, and 1% significance levels. But I said we can think of significance levels as confidence levels as well. So the 10, 5, and 1% significance levels correspond to 90, 95, 99% confidence. So what I could really say here is I can reject the null hypothesis with 95% confidence, but if I wanted to say it with 99% confidence, I can't. I would fail to reject the null at the 99% confidence level. Okay? Any questions over any of that? Okay. Also on Zoom, if for some reason the audio starts sounding really weird or like robotish, Wednesday I had a problem with it and someone didn't let me know for like a minute, and so then I had to like splice the video and use other sections to. So let me know if the audio ever starts going kind of wonky. I just have to retest it. So, all right. So, kind of finish that example out. All right, we got that p-value and we made our rejection decisions there. Okay. Oops. Let's go through an entire other example and we kind of break down each step here. So let's say that someone kind of puts out that the average back-to-school spending is $606.40. You don't really think that it's that amount. You think maybe it could be higher, it could be lower. But I think that it differs from that amount. Right? So I take this sample of 30 families. I get a sample mean of $622, and I somehow know the population variance for back-to-school spending, right? Maybe based off historical data. So if I want to test for whether or not it is different than this stated amount of $606, what would my null and alternative hypothesis be there? So last class I mentioned, anytime we see this kind of phrase of like different than, we should be thinking about what null and alternative hypothesis, what sign should be there. Equals to and not equal to, right? So if we just want to know, is it different than this value of $606 that this trade group stated, well, I'm thinking about what I want to find is that population mean not equal to that 606 reported amount. Which means I'll stack the deck against myself, I'll assume it is that value. I'll assume that the population mean is equal to $606.40, okay? So I've got what type of tail test here? Two-tailed test, right? That's pretty easy to tell when I have that not equal to sign in my alternative hypothesis or that equal sign in my null. I have a two-tailed test. So I could see a sample mean that's above or below that stated value of $606, and it would go against the null, right? If I see it above or below, it doesn't matter, right? Both sides, I could have evidence that goes against it. Okay? So how would I find the p-value for this test, right? Well, I've got my sample mean, I've got my population variance, and I know my sample size. So I can start to think of this as, I know that my sample means, if the assumed true value is in fact the true population mean, they will be normally distributed around that assumed true population mean. I could even think about what would the standard deviation be for this? Well, it's just the square root of my population variance, which was 4,225, divided by my sample size. Right? I could find that right away if I wanted to. What I then want to do is think about, okay, I forget, was it $622.85 maybe? If I'm a little off on the change there, it's okay. Now, I can find the probability that I found sample evidence that went against the null hypothesis or anything that was even further from that assumed true value, right? Now, the problem is, if I'm thinking about the probability I saw something this far away from the assumed true value, that went against the null, well, it was equally as likely that I could have seen a value that was exactly the same distance away from this assumed true mean, but below it. But for a two-tailed test, this would have also went against the null, right? So I'm really thinking about the probability that I saw sample evidence that goes against the null hypothesis that was that far away from the assumed true mean, or even further, is really going to be, I'm going to have an area on either side. Now, for a left or right tail test, we didn't have that because the p-value is the probability I saw something that went against the assumed true value, that was that far away from the assumed true value, or even further, that went against the null. When I looked at the other side, well, that would have actually been sample evidence that supported the null. But for a two-tailed test, that's not the case. Right? So what we can do is turn that sample mean value we found into a test statistic. Now, I can remember I'm going to have two tails. So once I find the area in one tail, to get the total value, I know that I'm looking at kind of the value that's the same distance away but below. So they're going to be symmetric distribution. So those are going to be the exact same area. So once I find the area in one tail, I can just multiply it by 2 to get my total p-value for a two-tailed test. Okay. So we've got our equation for the test statistic, right? That's always going to be the same. We just plug our values in. This should be, this is just a matter of getting this entered into our calculator correctly, right? Take the sample mean we found, subtract the assumed true mean, divide by the square root of our population variance over our sample size. Or if we had already done that and found that standard deviation of our sample means, we could have just plugged that value in for the entire denominator. Remember, what's in this denominator, this equation in the denominator, really just represents the standard deviation of our sample means. Okay? So we can do that, either way. All right, so once we have that test statistic, 1.39, we'll go to our table. So 0.09 is all the way at the end. So 1.39, 0.9177, right? So 0.9177 times 2 will be my p-value, right? No, it makes no sense. A p-value is a probability. If I multiply 0.9 by 2, I'm going to have something over 1. What the table told us was the entire area to the left, right? So for a two-tailed test, when we have a positive test statistic, it gets a little tricky because we have to remember, well, when I look that up, it's going to be the area to the left. I wanted the area to the right. So I have to subtract it from 1. But even after I subtract it from 1, I only have the area of one of my tails. To get my total p-value, I then have to multiply that by 2. Okay? Any questions on that? We could even complete this, right? We found that that test statistic was 1.39. Okay? I didn't walk through too much of how we just plug the numbers into that test statistic because, I don't know. I think that step's a little bit less crucial, right? I think if you have the equation in front of you, like you will for the exam, or you could have it for the homeworks. It's on the slides, and I've written it down a couple times. You're really just plugging your values into that equation. Okay? Any questions on that? We're okay with this? Okay. Where are we at on time? I don't know how I want to do this today. So I'll go through two things. We have examples, that first example we went through and then this second example. So we can kind of think about the role of alpha here. All right? So, oops, I can get it, there we go. So for that first example, we kind of already walked through this, right? I use different alpha values. I think I used 0.05 and 0.01, but we could use these three alpha values. If my p-value for that first example is 0.0132, right, I could reject for an alpha of 0.2, which would be the 20% significance level, or what level of confidence? 80% confidence. I could also reject, because that p-value is less than an alpha of 0.1 at the 10% significance level, or a confidence level of 90. But then I failed to reject at the 99% confidence level, or alpha of 0.01, 1% significance level. Okay. For the second example, if I actually do the math here, right, 1 minus 0.9177 times 2, I get a p-value of 0.1646. Okay. So I look at that p-value. It's less than my alpha of 0.2, so I could reject with 80% confidence. But at an alpha of 0.1, it's not less than 0.1, so I would fail to reject. Right? And if I can't say something with 99% confidence, I don't even have to check these other ones, right? If 0.16 isn't less than 0.1, well, it's not going to be less than 0.05 or 0.01. If I can't say something with 90% confidence, I sure as hell can't say it with 95 or 99%, right? So once you kind of find that alpha value that you're no longer able to reject the null at, you know that every alpha value below, you won't be able to reject, right? Once I find that kind of cutoff. And what would that cutoff alpha be? What would actually be wherever my p-value is, right? Just right below the p-value would be the first alpha that I couldn't reject, right? Because then my alpha is less, then my alpha ends up being kind of less than my p-value, which I need my alpha to be greater than, or the p-value to be less than alpha. Right? It's another way to think about. I think about this. Yeah, so I think I'll leave that there before we get in that discussion. Are there any questions on that before we keep moving? Okay. I think instead of doing stuff in Excel, I want to try to make sure we get through this today. So I'll go over this first. If we have time, I'll do a little bit of things in Excel today. If not, we'll hold off and do it Monday. So we can do this hypothesis testing for where the true kind of different assumed true values for the population mean. But we can also do it for proportions, right? It looks exactly the same. It's just instead of a true population mean and an assumed true population mean, we're going to have a population proportion and an assumed true population proportion. We still have the same three types of tests: greater than, less than, or right tail, left tail, and then a not equal to or a two-tailed test. Right? Same three types of tests. We look up the p-values the exact same way. The only thing that's going to be different is we'll have a different equation for our test statistic. So why would we have a different equation for our test statistic? Remember, how are we finding that test statistic when we had that sample mean? We took the sample mean, subtracted the assumed true population mean, divided by the standard deviation of our sample mean. Now we had an equation for this, which was the square root of population variance over my sample size. Okay. Well, if I'm dealing with proportions, I'll take my sample proportion, subtract the assumed true proportion, and divide by that standard deviation of my sample proportions. Now, when we were doing confidence intervals, this equation was p hat times 1 minus p hat over my sample size. But remember, we were only using the sample proportion there because we didn't know what the true population proportion was when we were building a confidence interval. Now, we still don't know the true population proportion, but what do we now have? We now have an assumed true population proportion. So I'm no longer going to be using my sample evidence because I've assumed this is the true value. And if that was in fact the true value, the variance, the standard deviation of my sample proportions should be based off that true value. Okay? With confidence intervals, we just had to use the sample proportion because it was the best estimate that we had. We no longer need an estimate because we have an assumed true value. Okay? So these test statistical equations, right? Like when I write them out, I could just plug these formulas into the denominator. But really, the process of constructing these test statistics, it's still following that same process that we've been using to calculate z-values, right? Subtract the mean, divide by the standard deviation of whatever statistic that you're interested in. Okay? All right, so we're going to do something a little bit different here as I work through these sample proportion examples, right? Or these hypothesis testing for proportion examples. I said last class, you might not remember, we had two approaches we could use. The p-value approach, which is what we went over last class and today, but then also the critical value approach. So the critical value approach, the first two steps will be the same. We have to figure out what our null alternative hypothesis are, figure out what type of test we have, specify the alpha that we want to test against. Now we can do several here, but here it's going to be important that we do know what alphas we want to look at. Using alpha and the type of test, I will then find my critical value and determine where my rejection region is. So I'll explain how we do this in a second, but this is the step that looks different, right? So even before I calculate my test statistic, I could find these critical values and rejection regions. Excuse me. I then calculate my test statistic, which we just set up on the board here, right? Here's our new equation when we're dealing with proportion examples. And then what I'll do is, if I have this critical value and rejection region, I will plot where that critical value is. I will then kind of plot where that test statistic is. If my test statistic or Z statistic is in that rejection region, I reject the null. And if it's not, I fail to reject the null. Right? So that's kind of our last step, is comparing those critical values and my test statistic or my Z statistic. So the idea of what we're going to be doing here is, and I'll explain the process of how we actually find the critical value here in a second. But what we're really doing is, we're going to be looking at that standard normal distribution. Right? We're going to find some cutoff value or some critical value and say, okay, look, if I see anything above this critical value, any test statistic, any Z statistic above this critical value, so if my Z statistic is here, well, this was my rejection region. So if my test statistic ends up being in that rejection region, I reject the null. If I see sample evidence that leads to seeing a test statistic somewhere down here, well, then I'm going to fail to reject the null. Right? That's kind of what's going on with that fifth step, right? When we're comparing our test statistic to where that critical value and rejection region are. So you can think about this critical value as really just like a cutoff value. If I see any test statistic greater than that critical value, I'll reject. If I see anything below it, I'll fail to reject. And what I said there holds for a right-tailed test. We'll have to go through the other tests here in a second. Things vary a little bit. And I kind of already explained, right? Now we can use that assumed true population proportion. So we're trying to find this critical value. How are we going to do that, right? So really this critical value is going to be the cutoff value that gives us kind of alpha in our tail. If we're dealing with a left-tailed test, it'll be the value. Remember, it's coming from a standard normal distribution, so it is going to be a Z value. Like it's a Z value. It comes from the standard normal distribution. It's going to be the Z value, right? That is the cutoff that would give us alpha for a left-tailed test in the left tail, for a right-tailed test in the right tail, and for a two-tailed test, it gives us alpha total in the tails. Okay? So that's the idea of this critical value. Okay? So if we think about a right-tailed test, well, if I'm trying to get alpha, we typically see kind of these small values, right? I know that for these right-tailed tests, I'm going to be finding positive critical values. And so there, just like I had it drawn up on the board, what I'm really thinking about is, if I see a test statistic greater than my critical value, then I would reject. Now, the difficulty gets in, if I'm dealing with a left-tailed test, my critical value is giving me alpha in the tail here. But for a left-tailed test, now my rejection region is anything to the left of this critical value. So now I only reject if I see a test statistic that is less than, right? Because it's a larger negative value. So another way you can think about this is, if I were to take the absolute value, no matter what type of tailed test I have, what I'm really looking for in every scenario is the absolute value of my critical value less than the absolute value of my Z statistic. If it is, I'll reject. Right? Now, mathematically, this is a good way to remember it. Personally, if I was doing these, just draw it out. If we draw it out, no matter what type of tailed test we have, we don't get confused with, okay, it's less than for left tailed test, greater than for right tailed test. for just plotting these values, it's pretty easy to see if your test statistic is in your rejection region. Okay? So to kind of be complete here, though, all right, we could write this out. Right? If it's less than for the left tail test, greater than for the right tail. And then for the two-tailed test, well, there we're going to have to take the absolute value anyways. And so really what we're checking for is the absolute value of my test statistic greater than the absolute value of my critical value? That would work for every single one of these tests. Okay? Any questions on anything up to this point? Okay. Now, I have kind of a summary here, but I'm going to show you how we find these critical values and then explain kind of what's going on here. So if we think about for a left tail test, I typically look at alphas of what? 0.1, 0.05, and 0.01. Those are kind of my benchmark or my cutoffs. If I want the value, the critical value that is coming from a standard normal distribution that gives me alpha in my tail, well, if alpha is a relatively small, relatively low probability, what's going to be true about these critical values? Well, the standard normal distribution, remember, has a mean of 0. So for a left tail test, my critical values are always going to be, if they're to the left of 0, they're all going to be, well, the area to the left of 0 is 0.5, right? I'm looking for these areas of 0.1, 0.05, and 0.01. So these critical values will have to be something less than 0 or negative, right? Now, if I had a large enough alpha, right? If my alpha got greater than 0.5, well, now I'm all the way over here. Well, that won't make sense for anything that we're doing. I mean, we want to be able to say things with high levels of confidence, right? Which correspond to lower levels of significance. Right? If I want to say, if I choose alpha of 0.8, what's my confidence there? It's kind of weird. 20%. Okay, you can say something with 20% confidence. That's not very bad. Like, that's not useful, right? So we're always going to be dealing with these small levels of alpha. So for a left tail test, all these critical values, right, are going to be negative. Right? Now, if I'm dealing with a right tail test, and I want alpha in my tail, what's going to be true about these critical values? They're always going to be positive. What about a two-tailed test? Two-tailed test, I'm going to have two tails, which actually means I'm going to have two critical values such that alpha total is in the tails, which means alpha over 2 will be in each tail. So here I'm going to have the same critical value, but one negative and one positive. Okay? Now, how do I actually find what these values are? We'll do the kind of harder one first. Let's do the two-tail. Let's say I wanted an alpha of 0.1. What area is going to be in each of these tails here? Well, if it's alpha over 2, 0.05. If I know that I want 0.05 in this lower left tail, how could I find that critical value if it's coming from a standard normal distribution? Just go to my table, right? If I'm dealing with a standard normal distribution, I know the area in the lower left tail is 0.05. I go here, I find the area of 0.05 in my table. It's in between these two values, negative 1.64 and negative 1.65. So same kind of thing with confidence intervals. We'll just take the higher of the two. And kind of, sure enough, see when we're dealing with a less than or left-tailed test. Sorry, not less than left-tailed. The two-tailed test was the example we had, right? When I look up an alpha of 0.1, I get 1.65. Now, when we looked it up in the table, we found negative 1.65. But that's because we were looking for 0.05 down here in that lower left tail. We have to remember for a two-tailed test, we also have that critical value over here on the right side as well. So we have kind of a pair of critical values for a two-tailed test. And we would do the same thing. If I wanted to look up the critical value for 0.05, well, now alpha is 0.05. That's the total area in my tails. So in each tail, I would have what? Alpha divided by 2, 0.025. I look up 0.025 in my table, and I'll find, to get a smaller area, right, 0.025, you could look up and find that critical value. It's going to be kind of more extreme there. So that's a two-tailed test. Let's look up a critical value real quick. If I'm dealing with a right-tailed test, because those ones are kind of hard. Okay? So let's say I wanted an area of 0.01 in my upper right tail. How could I find that? Remember, these critical values are coming from that standard normal distribution. So how would I look up the value that gives me 0.01 in the upper right tail? I'm using that table. Do I just look up 0.01? The table tells me the area to the left. What do I want here? I want 0.01 in the upper right tail. So I have to find the value that would give me 0.99 to the left, because that also means it would give me 0.01 to the right. Right? So I go to my table, look up 0.99. Looks like it's in between these two values here. So 2.32 and 2.33. So we'll take the higher of the two. Oh, I didn't want to do that. So sure enough, if we go right-tailed test or greater than test, alpha of 0.01, 2.33. And this kind of has a summary if you looked up every single one of those values for every different type of tailed test, right? We're going to see that they're always the same, because if I look up the same alpha, the same area in the tail, I'm always going to find the exact same z value corresponding to that when I go to the table, right? So these values will always be the same for these tests, right? So for a greater than test and a left-tailed or a less than test, or here greater than was a right tail, it's the exact same values, but for the right-tailed test, those critical values we said will all be positive. For the left-tailed test, they would all be negative. But they're the exact same value, right? Because if I wanted 0.01 in that lower left tail, if I look that up in the table, I'm going to find negative 2.33, because remember, it's a symmetric distribution, right? So, if you want to cheat, I guess it's not cheating, but, instead of looking up 0.99, if I look up 0.01 here and find negative 2.33, but then say, oh yeah, I was looking it up for a right tail test, so I know it'll just be that value, but positive. You could do it that way as well, right? Whichever way kind of makes most sense to you. Okay? Any questions over any of that before we keep on moving here? So this is kind of a summary, right? We're looking up. We always know that we're going to have positive critical values for a greater than or a right tail test, negative critical values for a left tail or a less than test, and they will be the z values that give us alpha in whatever tail we're looking for, right tail or left tail. Then for a two-tailed test, it's going to be a pair of critical values, right? So a positive one and a negative one, such that it'll be the value that would give us alpha over 2 kind of in both, right? Alpha over 2 in the right tail and alpha over 2 in the left tail. Hopefully kind of drawing that out kind of gives you an idea of how we're finding these, how we're looking them up using the table. And they're always going to be the same values, right? So we'll start seeing these pop up a lot. We'll probably start getting pretty familiar with these values. Okay? All right. So once we have those critical values, I kind of said we need to make this rejection region as well. Now, if you notice when I'm going through these, when I had my critical value, I always kind of thought of it as the rejection region as like going further into the tail, right? But really what I'm doing there, and I'll start to use this terminology because for a left-tailed test, I was actually going to smaller numbers, so less than, and for right-tailed, it was greater. I always just say like the rejection region is, do I see something that's more extreme than my critical value or larger in absolute value, right? Or anytime I plot that critical value, doesn't matter for what type of tailed test it is. Another way you could, this probably isn't technically a great way to say it, but like if I have a right tail test, find my critical value, draw an arrow into the tail. If I have a left tail test, I find my critical value. My rejection region is like going into the tail. If I have a two-tailed test, I've got two critical values here. Draw arrows going into both tails, and that's my rejection regions. Right? Now, when I calculate my test statistic, all I'm doing is plotting it, right? If I have a value here, hopefully I can plot the test statistic and see is it greater than or is it not, I can just plotting it on a number line. And if it falls in that rejection region anywhere, then I can reject. And if it doesn't, then I'll fail to reject, right? So I think this one visually is a little bit easier than the p-value approach. Because if I'm drawing this out, it becomes pretty clear if I plot those values, is my test statistic in that rejection region, okay? And we can use, just as a kind of clarification, I put this on here to make sure that we know we can use the p-value approach with proportions or with sample means, and we can use the critical value approach with sample means or sample proportion. Doesn't matter, right? Both these, it's just that I showed you kind of only one way, all right? So I didn't have to like go through them multiple times. I mean, we'll end up going through them multiple times anyways, but just I wanted to make sure that was clear. Okay? So I've kind of already talked through a lot of this, right? The critical value is really just the value that's going to give us alpha in the tail that we want, right? Right-tailed test, we're looking, or greater than test, we're looking at the right-tailed. Less than test, we're looking at left tail. And that's why I call them right and left tailed tests instead of greater than, less than, because it's a little bit easier to remember, right? But I also think like less than left tailed, greater than right tail, it's kind of easy to remember. Here's just kind of a summary of what I had in the board if you're going back through the lectures, just to kind of remember. And then here's another summary of our steps. So I also wanted to point out, I think I had this written slightly differently before when I introduced this idea. You can really flip-flop steps 3 and 4. I can calculate my test statistic first, then get my critical value and rejection region and plot my test statistic, or I can find the critical value and rejection region first, then find my test statistic and plot it. So it doesn't matter if you kind of flip-flop steps 3 and 4 there. So we could work through an example here, but I think I want to make sure I save enough time here. So we'll work through this example a little quick so I can have some time to explain a concept I think is important for today. So let's say I want to test for whether or not more than 50% of people own a gun. So what you want to test for is your alternative hypothesis. So if I want to find that more than 50% or greater than 0.5. So I'll assume the opposite is true, which is that it's less than or equal to 0.5. Right? So I've got what type of tailed test here? Greater than sign of my alternative hypothesis, so a greater than or right-tailed test, yeah. So I then, what are my critical values going to be? Well, first of all, if I have a right-tailed test, which of these can I rule out right away as being my critical values? Yeah, so the critical values have to be positive, right? So if I really want all three, I could look up one here and figure out whether or not A or C is the right answer, right? So I'm going to could look up 0.1, right? So I want 0.1 in my upper right tail, which means I want the critical value that gives me 0.1 here. So instead of looking 0.1 up in the table, I would actually want to look up 0.9. Right? If I do that, hopefully you're getting used to seeing, working with that table. If I do that, I'll end up finding 1.29. And we'll go through more examples where I do walk through and show you how to find it on the table. But at this point, it's really just look up 0.9 in that standard normal table and find the corresponding z-score. Right? If I then plotted those different critical values, the only other step I have now is find that test statistic and kind of plot against those. Right? Well, here I end up finding a negative test statistic if I plug my values into that test statistic equation. Well, if my critical values that I'd found were 1.29, 1.65, and 2.33, so here's my rejection regions, and I found a test statistic over here, very clearly I'm going to fail to reject. But if I just looked at the original problem, I want to point this out. here's my null hypothesis, that the true population proportion is less than or equal to 0.5. I found a sample proportion of 0.41. That sample proportion supports the null. So am I going to reject the null? No, I found evidence that supports it. Now, if I walk through all the steps and I find my critical values and I plot them, right, and I draw out my rejection regions, I calculate my test statistic and I plot it, well, very clearly I can see that, yeah, I'm going to, by far and away, I'm going to be failing to reject this null, right? But it just kind of made sense because I actually found sample evidence that supported the null. So I didn't really have to go through this entire process because I knew right away once I saw that sample evidence it supported the null. Even if I walk through the steps, it's going to lead me to the decision that I'm going to be failing to reject that null. Okay? So I want to try to go through something here in the last couple minutes. Kind of lets you see why the critical value and p-value approach will kind of result in the same decision. So if we think about what we were doing, is when I was looking up a p-value, I had this z statistic, and I was finding, let's do this just for a right-tailed test just to make it easy. I was finding my p-value. Right? The area to the right of that for a right-tailed test is my p-value. I then can think about, when I look up a critical value, it corresponds to whatever alpha I'm interested in, or whatever significance level I'm interested in. So remember, I was saying, if that test statistic, right, we can think about for the critical value, here's my rejection region. If that test statistic was greater than my critical value here, right, then I'd be rejecting, because then that test statistic was in my rejection region. But notice, if my test statistic is anywhere in this rejection region, then the area to the right of that test statistic, or that z statistic, which represents my p-value, any test statistic in this range will have a p-value that is less than alpha. So you're really just like comparing on a different axis, right? I can either compare these values on my x-axis, which represent kind of z values, or I can look at their corresponding areas to the right, but it, you know, I can compare the areas to the right, or I can compare the values. It'll still lead me to the same decision. So that's why it doesn't matter which approach we use, we'll still end up with the same rejection decision, right? Because the area to the right of our test statistic, that was our p-value, and the area to the right of our critical value, well, that's always going to be whatever alpha we've chosen, right? So I can compare the critical value to the test statistic, or I can compare alpha to my p-value. Okay? So I want to try to connect those two things before we end it today. Next week, we'll do a bunch of kind of see how we implement this in Excel. I'll also go through some more sample proportion examples. I know we hurried through that one today. I might even go over that one again or throw in a couple more sample proportion examples before we do some work in Excel on Monday. Okay? Any questions for me as we're ending here? All right. Enjoy your weekend, and I will see you on Monday.